Alrighty, this is my missile defense project. First off, this is my video. I'm just going to give a run through of it. A couple of things that I found important were when you see, if I'll play it in slow motion, you can see that as it gets shot on the left hand side, the rocket kind of takes a parabolic turn to the left, which was annoying trying to measure how far it actually went. Jeff dodges out of the way. And then over here I measured all of my points so I could figure out my velocities. I realized that the velocity, the maximum, or the initial velocity for the curve of a projectile was going to end up being one of the highest velocities as the velocity takes kind of a parabolic curve as the acceleration increases and then starts to decrease. So I brought up in Maple, I plotted some of my higher points that were consecutive, where this bottom axis is frame, so this is frame 9, 10, and 11, and 12, and this is my velocity. So there's a point here, and then a point way down here, point here, and a point here, and I figured that this drop, it makes it seem that the frame 9 had my highest velocity and my correct initial velocity, when it just seems like this point, I went back and checked it, but it seems like this point would just be an outlier, because you can see it follows a pretty nice little curve of falling velocity, which is exactly what it would do, how it would act if this was my initial velocity. So I assumed that was my initial velocity. Using that sports motion software, I found that my launch angle was pi over 4, 45 degrees. Like I said, I just assumed, based on reasoning about where the curve should be, that my initial velocity was 984.47. I set, this is the y form of the parametric equation, so as in like cosine whatever would be over here, and then this is only the y section. This 386.4, I computed the gravitational constant in feet. I computed it to inches, and that's where that came from. So and then I solved for t. I made a big T. I got 3.68 roughly, and that meant that the curve went back down to 0 and landed on what would be the y-axis or the ground in 3.68 seconds. And then, like I said, go back to sports motion. On the left-hand side, you can see the rocket kind of take what seems like a parabolic shape. It kind of launches and then falls over. So I don't know if it was due to the poor design of the rocket when it was trying to rifle itself, or the wind, or what it was, but so I assumed that it looks like, as the rocket kind of starts tilting more, it looks like whatever force is acting upon the rocket is giving it constant acceleration. So using a constant acceleration, I took the integral of it and brought it back, and we can see in Maple that this was my equation that I solved for, where A is obviously that universal acceleration that we didn't know what it was. T would be this big T, which is how long it landed, and plus 0.167 is important because you can see in the sports motion that as the rocket takes off, before it's reached what I decided was the initial velocity of the projectile, it's already curving a little bit. So you can see instantly it's already curving. So I wanted this T to represent, instead of just the projectile, I wanted it to represent the constant acceleration since it actually was fired, instead of when it reached the initial projectile velocity. And so I set that equal to 209.36, which is what I measured using Jeff's height. I measured over here. It was like right here where I measured him. I measured him at, he's 6'1", and so since he was kind of slouching, I measured him at 6 foot right here, and then measured this distance across to be 209.36 inches, and so that helped me. So I kind of set this constant acceleration to 209.36, which is what you can see in the equation here. Solved for that. Did some algebra off the screen. It was 28, roughly 28 was the constant acceleration. So this was my curve where I had this. I just stole from the original projectile equation, and this is my left-right term where I had set the gravitational or the acceleration, whatever it was, I solved for it, and this was my, with respect to y, my parametric equation. This 58.82, using the sports motion, I measured this distance where it reached initial velocity to be 58.82 inches, and I wanted to factor that in because I thought that it would make it a more accurate equation. And so when I plot this equation, I have something that looks a little bit like this, and you can see I'm going to shoot it off really quick. There it goes. Boom, lands. Okay, so you can see this is what I did with that plus 58 point something. That there's a little bit of gap over here, and that is because as it's fired, this is not really predicted by the equation since it's an acceleration. So that's where it actually reached its initial projectile velocity, and there it is. And let me turn it around for a different angle for you. You can see that it really, we'll play the sports motion one again, but it really looks pretty similar to the actual equation. We'll jump back to that one really quick. Oh, and see, you can see the path of the projectile takes that route. And so when I solve for plugging in for that equation, let me go back to this. Plugging in for this equation to see my final, plugging in for here equals 0 to see what I got for my final distance, it ended up being, plugging in this t number that we had solved for when y equals 0, and I got approximately 2,565.77 inches, because that's how everything is measured, which I converted to 213.814 feet, which is really ridiculous because my final distance ended up being 66 feet 5 inches, and what I computed by the curve was 213.814, which is a really significant difference. The only reason I can attribute to that would be the fact that after the rocket loses all its water, it really has very little mass. It can be pushed around by whatever gusts of wind or whatever there is in the air, and that might have affected also, drag with the aerodynamics of the rocket. I'm not a physicist, but it seems to me that all those extra variables would only decrease how far the object went, and so that's why my estimation ended up so high.